Ever wonder why standing by a campfire on a cold night feels, well, different from standing the same distance from a heat lamp? Or maybe why a room can feel kind of chilly, even if the thermostat says it's perfectly warm? Today we're taking a deep dive into the fascinating, often unseen world of radiation heat transfer. And we're going to focus specifically on something called view factors. Our mission really is to unpack how the orientation and the geometry of surfaces profoundly impact how heat actually moves between them. Understanding these view factors, it's like a shortcut to being well-informed about how engineers and scientists tackle these real-world heat transfer challenges. Everything from designing massive industrial furnaces to just ensuring your personal comfort right in your own home. We pulled some surprising insights and practical applications from a pretty comprehensive textbook chapter on this. And yeah, we're ready to guide you through them. Okay, so let's unpack this a bit. When we talk about radiation heat transfer, it's not just about how hot something is, right?
Exactly. That's part of it, of course.
But it's also really critically about where it is in relation to other things and how it's oriented. Is that right?
Precisely. The geometry is key.
Think about like a simple example.
Yeah.
A camper by a fire. You instinctively turn your front to the fire, not your side, to get warmer.
Yeah.
Or sunbathing, you lie flat, expose more skin. Why?
Well, it's all about how much of the radiation from that source can actually see your surface, how much directly hits you. And what's fascinating here is that this intuitive understanding, it translates directly into a precise scientific concept. It's called the view factor. You might also hear it called the shape factor or configuration factor, sometimes even angle factor. Lots of names.
Okay, view factor.
At its core, the view factor, we usually write it as phi, is simply the fraction of radiation leaving one surface, let's call it surface I, that directly hits another surface J.
Directly. That seems important.
It is. The key here is directly. It's purely a geometric quantity. It doesn't depend on what the surface is made of, or its color, or temperature. Not for the view factor itself. We usually assume the surfaces are diffuse, which just means they radiate and reflect energy sort of evenly in all directions.
So it's all about the lines of sight between the surfaces then. And you emphasize directly. Does that mean reflections don't count?
Exactly right. View factors only consider that direct line of sight radiation. If radiation bounces off, say, a third surface before hitting the target surface J, that bounce isn't part of the feed calculation.
Good.
We handle those reflections later when we calculate the total heat transfer. But the U factor itself is just the direct shot.
What about a surface seeing itself? Can that happen?
Yeah.
Seems a bit weird.
That's actually a really insightful question. It can happen. For flat surfaces like a wall or convex ones like the outside of a pipe, the view factor from that surface to itself, phi, is 0. It just can't radiate directly back onto itself. There's no line of sight.
Makes sense.
But for a concave surface, like the inside of a bowl or a sphere or maybe a U-shaped channel, phi is definitely non-zero. Parts of that curved surface can see other parts of itself directly.
Okay. And this next point seems pretty crucial. Maybe clears up a common misconception. Can one surface see all of another surface? Like 100%?
Yes, it absolutely can. Consider two concentric spheres. You have a small one inside, surface 1, and a larger one enclosing it, surface 2. Every single bit of radiation leaving that inner sphere, surface 1, has to hit the outer sphere, surface 2. There's nowhere else for it to go.
Right.
So the view factor from the smaller sphere to the larger sphere, F12, is exactly 1. It intercepts 100%.
Okay.
But conversely, the view factor from the larger sphere back to the smaller one, F21, that's going to be less than 1.
Why is that?
Because the larger sphere also radiates to other parts of itself, if it's concave, or just out into space if there are openings. It doesn't all hit the small inner sphere.
I see.
So this just highlights that view factors, phi, always range between 0 seeing nothing and 1 seeing everything possible from that surface.
Okay, so calculating these view factors for every pair of surfaces.
Yeah.
It seems like it could get pretty complicated pretty fast, especially if you have lots of surfaces in, say, a furnace or something. How do engineers actually handle that without just, drowning in calculations?
You're absolutely right. Directly calculating every single view factor using the basic definition, often involving complex integrals, can be incredibly tedious, sometimes impossible analytically. That's precisely why we rely on some fundamental relationships. Think of them as clever shortcuts or rules. They significantly simplify the whole process.
Rules, okay. Like what?
Well, first, there's the reciprocity relation. It's really handy. It basically says there's a symmetric relationship. If you know the view factor from surface I to surface J, and you know their areas, you can immediately find the view factor going the other way, from J back to I. The relationship is AI phi equals A J phi.
So you only need to calculate it one way.
Often, yes. If one calculation is easier than the other, you do the easy one and use reciprocity to find the reverse view factor. It's a powerful shortcut.
Nice. What else?
Next up is the summation rule. This one comes from basic energy conservation. Imagine any enclosed space, like a room or a furnace made up of n surfaces. All the radiation leaving any single surface, let's say surface I, must be intercepted by some surface within that enclosure. That includes hitting itself if it's concave, right?
Right, phi that we talked about.
Exactly. So if you add up all the view factors from surface I to all other surfaces, J1 to N, including phi, the total must be exactly 1.
100%. All the energy has to go somewhere.
Precisely.
So if I have, say, a 6-sided cubical furnace, I don't need to manually figure out all 36 possible view factors directly. That sounds like a massive time saver.
It is. For that 6-surface enclosure, you might only need to determine maybe 15 view factors directly using formulas or charts. The remaining 21 can be found just using the summation rule and that reciprocity relation we just discussed.
Wow.
For example, take a simple cubical furnace, 5 meters by 5 meters by 5 meters. Let's look at the base. Surface 1, it's flat, so it can't see itself. F11 is 0.
Okay.
Now let's say we calculate or look up the view factor from the base 1 to the top 2 and find F12 is 0.2. The summation rule for the base says F11 plus F12 plus F1 sides equals 1. So 0 plus 0.2 plus F1 sides equals 1. That means the view factor from the base to all 4 side walls combined must be 0.8.
Without calculating each side individually. That's clever.
It simplifies things enormously.
That's incredibly helpful. What if surfaces aren't, simple whole units? What if they're broken up into parts, or you're only interested in radiation to a specific section?
Good question. That's where the superposition rule comes in. It's quite intuitive, actually. It says the view factor from a surface I to a larger composite surface. Geoimagine J is made up of 2 smaller parts. J1 and J2 is simply the sum of the view factors from I to J1 and from I to J2.
So you just add up the views to the part.
Exactly. Phi run J1 plus J2, phi minus J1 plus phi minus J2. Think of it like this. Imagine you need to find how much radiation leaves the circular base of a cylinder and escapes through a specific ring-shaped opening at the top.
Okay, like an annulus.
Right. You probably don't have a direct equation for the view factor from a disk to a ring.
Probably not, no.
But you do have equations for the view factor from a disk to another coaxial disk. So you can think of the ring as the difference between a larger disk, outer edge of the ring, and a smaller disk, inner edge of the ring.
Ah, subtraction.
Precisely. If the view factor from the base to the larger 8-centimeter radius circle at the top is, say, 2.28, and the view factor from the base to the smaller inner 5-centimeter radius circle is 0.11, then the view factor from the base just to the ring itself is the difference, 0.28 minus 0.11, which equals 0.17.
That makes calculating tricky shapes much more manageable.
It does. It lets you break down complex geometries into simpler ones you already know how to handle.
That makes so much sense.
Yeah.
Any other clever tricks for handling shapes, especially if you have, identical sides or something?
Absolutely. Symmetry is your friend here. The symmetry rule is incredibly useful. It simply states that if 2 or more surfaces, let's call them J and K, are symmetrical with respect to another surface, I, then their view factors from that surface will be identical. Phi J must equal phi K.
Okay, so if they look the same from surface size perspective.
They get the same amount of radiation fraction.
Yeah.
Exactly. Think about a pyramid with a square base. Let the base be surface 1.
Go.
The 4 triangular side surfaces are obviously symmetrical with respect to the base.
Right, they're identical.
So the view factor from the base to any one of those side surfaces is exactly the same as the view factor to any other side surface. Now, we know the base is flat, so F11 is 0, and the summation rule says F11 plus F1 to side 1 plus F1 to side 2 plus F1 to side 3 plus F1 to side 4 equals 1.
Since all 4 side view factors are equal due to symmetry.
Each one must be 0.25, 1 divided by 4.
Exactly. You figured out the view factor to each side without any complex geometry, just using symmetry and the summation rule. That's really neat. So what about those really long shapes, like ducts or channels you see in industrial settings, like a really long triangular duct? The math seems like it could get hairy fast.
Yeah, for those kinds of infinitely long, essentially 2-dimensional geometries, there's another fantastic shortcut. It's called the crossed strings method. Sounds a bit strange, but it's amazingly simple and powerful. It was developed by a brilliant engineer named H.C. Hotel back in the 1950s, same person associated with gas radiation charts we might touch on later.
Crossed strings. Okay, intriguing.
Yeah.
Can you paint a quick picture of how this idea actually works?
Sure. Imagine two infinitely long parallel plates, maybe of different widths, facing each other.
Okay.
To find the view factor from, say, the bottom plate to the top plate, you literally imagine stretching strings between their edges. You connect the endpoints diagonally, those are the crossed strings.
Like an X between the ends.
Exactly. And you also imagine strings going straight across between the corresponding endpoints, those are the uncrossed strings. The method states that the view factor, phi, is equal to the sum of the lengths of those crossed strings, minus the sum of the lengths of the uncrossed strings, all divided by twice the width of the surface you're calculating from, surface I.
Wow, that's purely geometric, just lengths of lines.
Purely geometric. It's a surprisingly elegant trick derived from some clever calculus Hotel did. And the beauty is it works even if the surfaces share an edge or if there's another surface partially blocking the view between them. You just trace the strings around the obstruction.
That's incredible for those long, uniform shapes.
Yeah.
Okay, so we've got the geometric part down now, how surfaces see each other using these view factors and rules. That makes sense. But how does this view actually translate into heat moving from one place to another? This is where the engineering really kicks in, right? Getting to the energy transfer.
Great question. That's the whole point, after all. So we start by looking at an idealized scenario. Black surfaces.
Black surfaces. Okay, perfect absorbers and emitters.
Exactly. Imagine a surface that absorbs all radiation hitting it, reflects none, and emits the maximum possible amount of energy for its temperature, following the Stefan Boltzmann law.
Not very realistic, but a starting point.
Precisely. It simplifies the analysis greatly and gives us a baseline understanding. Real surfaces are more complex, but for two black surfaces, say surface 1 at temperature T1 and surface 2 at T2, the net rate of radiation heat transfer between them is actually quite straightforward to calculate. It's simply the area of the first surface times the view factor from 1 to 2 times the Stefan Boltzmann constant sigma times the difference in their absolute temperatures raised to the fourth power, T14, T24.
So area, view factor, and that T to the fourth difference.
That's it for black surfaces, a powerful, direct relationship. Let's quickly revisit our cubicle furnace example. Imagine all its surfaces are perfectly black. Let's say the base surface 1 is at 800 Kelvin, the top surface 2 is much hotter at 1500 K, and the sides, surface 3, are cooler at 500 K. We already know F12 base to top is 0.2 and F13 base to sides is 0.8. Using the formula, the net heat transfer from the base to the top would actually be negative, meaning heat flows to the base from the hotter top.
Because T2 is much higher than T1.
Right. It turns out to be around negative 1,300 kilowatts, a huge amount gained by the base from the top. And the heat transfer from the base to the cooler sides would be positive, maybe around 400 kilowatts lost. So the total net radiation heat transfer from the base is the sum. Negative 1,300 kilowatts plus 400 kilowatts plus 400 kilowatts equals minus 900 kilowatts.
Meaning the base is actually gaining almost a megawatt of energy net through radiation.
Exactly. Even though it's hot itself, the hotter top dominates the exchange. It shows how powerfully temperature drives radiation and how the net flow depends on all surrounding surfaces.
That's a huge amount of energy. But as you said, most real-world surfaces aren't perfectly black, are they? They reflect some energy. What happens then?
You're absolutely correct. Most real surfaces aren't black. They are typically modeled as opaque, diffuse, and gray.
Okay, what does that mean? Opaque is obvious.
Opaque means radiation doesn't pass through them. Diffuse means they reflect incoming radiation uniformly in all directions, like a matte paint finish, not like a mirror.
And gray.
Gray means their radiation properties, like how much they absorb or emit, are basically independent of the radiation's wavelength. It simplifies things compared to surfaces that absorb or reflect differently in different colors.
Okay, opaque, diffuse, gray. More realistic.
Yes. And when surfaces reflect, things get more complicated because radiation starts bouncing around. Here, a concept called radiosity J becomes critical.
Radiosity. Okay, what's that?
Think of it this way. A surface emits energy because of its temperature. That's called emissive power, E. But it also reflects some of the radiation hitting it from other surfaces. Radiosity J is the total radiation energy leaving the surface per unit area per unit time. It includes both the energy the surface emits itself plus the energy it reflects.
Ah, so it's emitted plus reflected.
Exactly. For a perfect black body, since it reflects nothing, its radiosity is just its emissive power, J equal E. But for a gray surface, radiosity is a combination of emitted and reflected energy.
So how does this concept of radiosity help us calculate the actual heat transfer, especially with all those tricky reflections bouncing around?
Well, it allows us to set up a really useful analogy. We can actually model this complex radiation heat transfer between diffuse gray surfaces using an electrical analogy. It makes visualizing it much easier.
An electrical circuit for heat, how does that work?
Think of the net radiation heat transfer as the current flowing. The potential difference driving this flow isn't voltage, but rather the difference in blackbody emissive power between surfaces. Each surface itself has a kind of surface resistance to releasing radiation. This resistance depends on its area and its emissivity. A surface with low emissivity, meaning it doesn't emit well, has a high surface resistance.
Okay, like a resistor connected to the surface's potential?
Kind of, yeah. And then the space between two surfaces, say surface I and surface J, has a space resistance. This resistance depends on their areas and, crucially, the view factor between them, phi.
So the view factor determines the resistance between surfaces.
Exactly. A high view factor, they see each other well, means a low space resistance, making it easy for radiation current to flow between them. A low view factor means high resistance.
That analogy really helps visualize the bottlenecks and pathways for heat flow.
Yeah, it does. And this network setup is particularly useful for understanding something called re-radiating surfaces.
Re-radiating, what are those?
Imagine a surface that's perfectly insulated on its backside. Maybe it's a thin sheet in the middle of a gap or a well-insulated furnace wall. No net heat can actually pass through it. So any radiation energy it absorbs from one side, it must re-radiate out from both sides to stay in balance. Its net heat transfer is zero.
So it just bounces the energy along in a sense.
Pretty much. Its temperature floats to whatever value allows it to re-radiate all the energy it absorbs. In the electrical analogy, a re-radiating surface acts like a node where current flows in and flows out, but it doesn't have its own connection to a fixed potential or temperature source, and its surface resistance is effectively bypassed in the net calculation.
Okay, that seems like it could simplify calculations in some cases.
It definitely can. If you have, say, an insulated wall in a furnace, treating it as re-radiating simplifies the resistance network. Now, for actually solving these network problems, there are two main practical methods. For simpler enclosures, maybe up to 3 or 4 surfaces, the network method, literally drawing the electrical circuit analogy, works great. You can often solve it by hand using circuit rules.
Visualizing it.
Right, but for more complex systems with many surfaces, that network gets messy fast. So we use the direct method, which used to be called the matrix method. This involves setting up a system of linear algebraic equations based on the energy balance at each surface, involving radiosities, emissivities, temperatures, and view factors. Then you solve that system, usually with a computer.
Okay, so network for simple, direct matrix method for complex.
That's the idea. And for some very common simple geometries like 2 surface enclosures, think of 2 very large infinite parallel plates, or 2 long concentric cylinders, things get much simpler.
How so?
Well, for 2 infinite parallel plates, surfaces 1 and 2, all radiation leaving surface 1 must hit surface 2, and vice versa, ignoring edge effects. So the view factor F12 is effectively 1.
Ah, okay. No need for complex view factor calculations there.
Right. And the resistance network simplifies dramatically. This allows for straightforward, simplified equations for the net heat transfer between them, involving just their temperatures, emissivities, and areas. For instance, remember those 2 very large parallel plates we mentioned? One at 800 K with emissivity 0.2, the other at 500 K with emissivity 0.7.
Yeah.
Using the simplified 2-surface enclosure formula, the net radiation heat transfer between them turns out to be about 3.6 kilowatts per square meter.
So we can get a precise number, even with reflections, for common setups.
Exactly. We can quantify how much heat is moving around.
It sounds like we've uncovered some really powerful tools for understanding radiation between solids. And it's clear that we can now pretty precisely calculate how much heat moves, even with reflections playing a role. This must have huge implications for practical applications, far beyond just designing industrial furnaces, right?
Oh, absolutely. The principles we've discussed pop up in many, many areas. One critical application is using radiation shields.
Radiation shields, you mentioned them briefly with the re-radiating surfaces. How do they work in practice?
Well, imagine you have 2 surfaces, maybe one hot and one cold, and you want to significantly reduce the radiation heat transfer between them. You can insert one or more thin sheets of material in the gap between them. The key is that these sheets should have very high reflectivity, which means they have very low emissivity. Think polished metal foils.
So they reflect radiation rather than absorbing and re-emitting it.
Exactly. Each shield you insert effectively adds more resistances into that electrical analogy network we talked about. It creates more barriers for the radiation current to flow through.
Like adding more resistors in series in a circuit.
Precisely. And the lower the emissivity of the shield, the more reflective it is, the higher the resistance it adds. The result is a dramatic reduction in the overall heat transfer.
Where would you use these?
They are absolutely essential in cryogenics for insulating tanks holding liquid nitrogen or helium. You use multiple layers, sometimes dozens of thin reflective shields in a vacuum. They call it multi-layer insulation, or MLI. They're also critical in space applications, protecting satellites and spacecraft from the intense heat of the sun or the cold of deep space.
And you mentioned temperature measurements, too.
Yes, we'll get to that. But first, just to show how effective they are, remember those two large parallel plates, one at 900 K, pretty hot, and the other at 650 K?
Mm-hmm.
If we place just one thin aluminum sheet, which has a very low emissivity, say 0.15 on both sides, right in the middle between them, the net radiation heat transfer between the original plates drops significantly, maybe from around 2,800 watts per square meter without the shield down to about 750 watts per square meter with the shield.
Wow, just one shield cuts it down to almost a quarter?
It does. And adding more shields reduces it even further, though the benefit of each additional shield diminishes slightly. This principle is also absolutely vital for safety in many industrial settings. For instance, think about an electrically heated drawbatch furnace used for heat treating metals. The inner heating elements might be at, say, 600 degrees Celsius.
Very hot.
Right, but the outer surface of the furnace door or casing needs to be kept below a safe temperature, maybe 45 degrees C, so workers don't get burned if they touch it.
Makes sense.
If you just had the hot inner surface and the cooler outer casing with air between them, even if they both had fairly low emissivity, say 0.1, the outer surface could still easily reach something like 174 degrees C due to radiation from the inside. Way too hot.
Definitely dangerous.
But if you strategically place multiple radiation shields, maybe 10 thin sheets with low emissivity in parallel within the furnace front assembly, you can dramatically reduce that heat transfer and keep the outer surface temperature safely below the 45 degrees C limit.
So the shields are basically thermal insulation, but working specifically against radiation.
That's a great way to put it. They insulate against radiative heat transfer.
That's a powerful demonstration of using these principles for safety. What other, maybe surprising ways does radiation impact things?
Well, another really significant impact, and one that catches people out sometimes, is on temperature measurements, especially when measuring the temperature of gases or fluids.
How so? You stick a thermometer in and it reads the temperature, right?
Not quite always accurately. When you use a thermometer or a thermocouple sensor to measure the temperature of a fluid, say hot air flowing in a duct, that sensor is exchanging heat in two main ways. It exchanges heat with the fluid itself, usually by convection. That's what you want it to measure.
Okay.
But it also exchanges heat directly by radiation with the surrounding surfaces like the walls of the duct.
Ah, I see where this is going. If the walls are a different temperature.
Exactly. If the duct walls are much colder than the hot gas, the sensor will radiate heat to the walls. This makes the sensor cooler than the gas it's trying to measure.
So the reading will be too low.
Correct. Conversely, if the walls were hotter than the gas, the sensor would absorb radiation from the walls, and the reading would be too high. The thermometer reads its own equilibrium temperature, which is somewhere between the true fluid temperature and the surrounding surface temperatures, influenced by both convection and radiation.
So the thermometer reading isn't necessarily the true gas temperature.
Often no, especially if the surrounding surfaces are at a significantly different temperature. To get the actual fluid temperature, you often need to calculate and add a radiation correction term to the measured thermometer reading.
How big is this correction usually?
It's most significant when the convection heat transfer between the fluid and the sensor is weak, like in slow-moving gases,
Right.
and when the sensor itself has a high emissivity, meaning it radiates strongly. For example, imagine a standard thermocouple, maybe with an emissivity around 0.7. Let's say it's placed in hot gas and reads 530 Kelvin, but the duct walls surrounding it are much cooler, maybe only 380 Kelvin. Because the thermocouple is radiating heat to those cold walls, its actual reading, 540 K, is lower than the true gas temperature. If you do the calculations, the actual gas temperature might be closer to 549 Kelvin, almost 20 degrees hotter than the reading.
Wow, that's a significant error.
It can be huge in some applications, but remember, radiation shields.
Yeah.
What if you shield the thermocouple? You put a small reflective cylinder around the thermocouple junction, but allow the gas to flow through.
Like a mini radiation shield just for the sensor.
Exactly. Maybe made of polished aluminum foil with a very low emissivity, say 1.15. Now, the thermocouple mainly sees the shield, which will be much closer to the gas temperature because it's bathed in the gas. It radiates much less heat away to the cold duct walls.
So the reading gets more accurate.
Much more accurate. With
Yeah.
the shield in place, the thermocouple might now read, say, 532 Kelvin, much closer to the true 549 K gas temperature. The shield minimizes that radiation error.
That's a clever application. Now, you mentioned comfort earlier. Here's where it connects directly to our everyday lives, isn't it? How does this unseen radiation affect us personally?
It's a huge factor, and one people often feel intuitively but don't always attribute to radiation. It's critical in human comfort, especially related to heating and air conditioning.
How so?
Your body is constantly exchanging heat with its surroundings, primarily through convection with the air and radiation with surrounding surfaces like walls, windows, ceilings, floors.
Okay.
Let's say you're indoors wearing light clothing. The air temperature might be a perfectly comfortable 22 degrees Celsius, about 72 F.
That sounds nice.
But what if the walls of that room are significantly colder? Maybe it's a poorly insulated building on a cold day, and the inner surfaces of the walls are only, say, 18 degrees Celsius, around 64 F.
Okay, the air is warm, but the walls are cold.
Right. Even though the air is 22 degrees C, your body will be radiating a noticeable amount of heat directly to those colder walls.
So you lose heat faster than you would if the walls were also 22 degrees C.
Exactly.
Yeah.
And that net loss of heat via radiation makes you feel chilly, even though the thermostat reading for the air seems fine.
I've definitely felt that.
Yeah.
A room that just feels cold despite the air temp.
That's often the radiation effect. To actually achieve the same level of thermal comfort, to feel as warm as you would if the walls were also 22 degrees C, you might need to crank up the air temperature significantly. If those walls were cold and you weren't wearing much, you might need to raise the air temperature to almost 27 degrees Celsius, around 80 F, just to compensate for their radiative heat loss to the cold walls.
Wow. So insulating the walls isn't just about saving energy by stopping heat conduction.
It's also hugely about comfort. Well-insulated buildings have warmer interior surface temperatures in winter.
Meaning you radiate less heat to them.
Precisely. And because you feel comfortable due to the warmer surfaces, you can often set the thermostat lower in winter, saving energy while still feeling perfectly fine.
And presumably the opposite in summer. Cooler walls help you feel cooler even if the air is a bit warmer.
Exactly the same principle applies. Well-insulated buildings allow thermostats to be set at a lower temperature in winter and a higher temperature in summer without compromising that feeling of comfort. It's all thanks to controlling that invisible radiation exchange between you and your surroundings.
That really brings it home. Okay, we've mostly talked about solid surfaces exchanging radiation up to this point, maybe with shields between them. But what about gases? Does the air around us radiate heat, or the gases inside a furnace?
That's a really important distinction to make. Most common gases, like the nitrogen and oxygen that make up the vast majority of the air we breathe, are what we call non-participating media at typical temperatures and pressures found in buildings.
Non-participating, meaning they don't really interact with thermal radiation.
Pretty much. They are essentially transparent to it. Heat radiates through air, but the air itself doesn't significantly absorb or emit thermal radiation under normal conditions. You don't feel heat radiating from the air in a room.
Okay, but you said most gases.
Right, because some gases, particularly those with asymmetric molecules, do participate significantly in the radiation process. The most important ones in engineering applications are water vapor, H2O, and carbon dioxide, CO2.
Greenhouse gases.
They are, and their radiative properties are key to that effect, but they're also crucial inside combustion chambers, furnaces, boilers, rocket engines, anywhere you have hot combustion products. These gases absorb thermal radiation, especially at moderate temperatures, and they both absorb and emit radiation quite strongly at the high temperatures found in combustion processes.
So a furnace that's full of hot combustion gases inside, that's a whole different ballgame for heat transfer calculations compared to just radiation between the solid walls.
Yeah.
Sounds incredibly complex.
It absolutely is. The presence of these participating gases complicates radiation analysis considerably for several reasons.
Like what?
First, unlike radiation from a surface, gas radiation is a volumetric phenomenon. It depends on the entire volume, the shape, and the thickness of the gas body, not just a surface area.
Okay, volume, not area.
Second, gases don't behave like the gray surfaces we discussed. They absorb and emit radiation very strongly, but only in specific, narrow wavelength bands. They are highly non-gray or selective.
So they interact differently with different colors or wavelengths of radiation?
Exactly, which makes calculations harder. And third, their radiative properties, how much they absorb or emit, depend strongly on the gas temperature, its pressure, and the specific mixture or concentration of the participating gases, like H2O and CO2.
Wow. Volumetric, non-gray, depends on everything. How do engineers even begin to calculate that?
It's definitely challenging. Direct theoretical calculation is extremely complex. So for practical engineering calculations, we often rely heavily on empirical data and correlations. Much of this foundational work was done by H.C. Hotelligan back in the 1930s to 1950s. He developed charts based on experimental measurements. These charts allow engineers to determine an effective total emissivity and an effective total absorptivity for a body of gas under specific conditions.
Effective properties, so like an average value that works for calculations.
Sort of. It's a way to approximate the complex reality. This effective emissivity, for example, depends on the gas temperature, the partial pressures of the CO2 and H2O in the mixture, and even the shape and size of the gas body. That last part is accounted for by something called the mean beam length, L.
Mean beam length.
Yeah, it's like an effective path length that represents the average distance radiation travels within the gas volume before escaping or hitting a surface. It depends on the geometry. There are formulas or tables for common shapes like spheres, cylinders, cubes, etc.
Okay, so you need temperature, pressure, composition, and this mean beam length to use the charts.
That's right. And for a gas mixture that contains both CO2 and H2O, which is very common in combustion products, the total effective emissivity isn't just the sum of their individual emissivities from the charts. You have to add them up, but then subtract a small emissivity correction factor.
Why subtract something?
Because the emission bands of CO2 and H2O overlap slightly in the infrared spectrum. If you just added their individual emissivities, you'd be double counting the energy emitted in those overlapping bands. The correction factor accounts for that overlap.
That makes sense. Can you give us a real-world example of how this plays out in, say, a furnace?
Sure. Let's imagine a large cylindrical furnace, maybe 5 meters in diameter and 5 meters high.
Okay, big furnace.
And it's filled with hot combustion gases at 1200 Kelvin, that's over 900 degrees C, and a total pressure of 2 atmospheres. Let's say the gas mixture, by volume, is 8% water vapor, H2O, and 5% carbon dioxide, CO2, with the rest being non-participating gases like nitrogen.
Typical combustion product.
Right. First, we'd calculate the mean beam length for a cylinder of these dimensions. Let's say it comes out to be around 3 meters. Then, using the gas temperature, 1200 K, the partial pressures of H2O and CO2, which depend on the total pressure and their volume fractions, and that mean beam length. We go to Hotell's charts, or use correlations derived from them. We find the emissivity of CO2 alone, the emissivity of H2O alone, and that overlap correction factor. For these conditions, the effective emissivity of the entire gas mixture radiating heat to the furnace walls might turn out to be approximately 0.45.
Okay, so the gas acts like a surface with an emissivity of 0.45 in terms of radiating heat.
Roughly, yes. That tells us how much it emits. Now, to find the net radiation heat transfer from these hot gases to the furnace walls, say, if the walls are cooler, maybe black surfaces at 600 K, we also need the gas's absorptivity.
How well it absorbs radiation coming from the walls.
Exactly. And this is another tricky part. Gas absorptivity is also found from similar charts, but it uniquely depends on both the gas temperature, 1200 K in our case, and the temperature of the surface emitting the radiation, the 600 K walls.
So absorptivity depends on the wall temperature too, not just the gas temperature like emissivity did.
Correct. For our example, using the charts again with both T-gas equals 1200 K and TWAL equals 600 K, the gas absorptivity might turn out to be about 0.64. Notice it's different from the emissivity, 0.45. Gases are not gray.
Okay, so we have an emissivity, 0.45, and an absorptivity, 0.64 for the gas. What's the practical upshot of all this intricate calculation? Can we now figure out the actual heat flow?
Yes, exactly. Now we can calculate the net rate of radiation heat transfer from the gas volume to the total surface area of the furnace walls. We use an equation that involves the gas emissivity, the gas absorptivity, the gas temperature, the wall temperature, the Stefan-Boltzmann constant, and the total surface area of the furnace walls, which for our 5 meter cylinder is about 118 square meters. Plugging in all those numbers.
Big number coming.
It is. The net rate of radiation heat transfer from those combustion gases to the cooler furnace walls turns out to be a very substantial 5.69 megawatts.
Wow. Nearly 6 megawatts just from the gas radiation.
Yeah. It highlights how incredibly important gas radiation is in high-temperature systems like furnaces and combustion chambers. It often dominates the heat transfer. And getting that number right, even using these empirical methods, is absolutely critical for designing efficient industrial processes, ensuring materials don't overheat, predicting fuel consumption, and ensuring overall safety.
What an incredible deep dive that was. Seriously, we started with something as simple and intuitive as standing by a campfire, and we ended up unraveling how this really quite complex physics, these view factors and then radiation rules, allows engineers to precisely calculate and control heat transfer. I mean, everything from massive industrial furnaces burning megawatts of power down to tiny temperature sensors, and even just understanding our own personal comfort.
It really does just go to show how something as fundamental as the geometry, the shape and orientation of objects, can have such profound and often surprising effects on how energy moves around. Effects that go far beyond what we might initially perceive just looking at things. It's truly a hidden dance of energy happening all around us.
So what does this all mean for you, listening in? Well, the next time you walk into a room that feels strangely chilly, even though the air thermostat says it's warm, or you notice those highly insulated, perhaps triple-glazed windows, you'll have a new appreciation for that hidden dance of radiation, and for the clever engineering that uses these principles to keep us safe, comfortable, and maybe even save some energy.
Indeed. And thinking about the future, it really raises an important question, doesn't it? Knowing just how much simple geometry influences heat transfer. How might really understanding and manipulating these view factors inspire completely new designs? Maybe for radically different types of sustainable architecture that passively managed thermal comfort? Or for cooling ever smaller, more powerful electronics? Perhaps even for specialized medical devices where precise non-contact temperature control is absolutely paramount.
That's a fantastic thought to end on. Something to ponder as you look around your own home or workplace and maybe feel just a little more well-informed about the unseen forces of radiation shaping our world.